But I thank you for the invitation. I do mean that. Um, and I hope that this is worthwhile. As I said to the organizers earlier, but for everybody's benefit, I actually wrote this out and I'm going to provide the plain text of this to them for distribution to you later. You're welcome to do with it as you like, sort of like that old Jay Leno commercial for Doritos. Eat all you like, we'll make more. Well, do what you like with this. We'll make more. So I'm going to begin. And I'm getting old enough that I have to wear glasses. The alternative, of course, is worse. Let's let that go. So anyway, I want to begin by saying I do very much think that what you're doing is important. It's really very important, and it is hard. And perhaps those two, important and hard, always go together. Certainly cybersecurity in that sense is hard. We have what I guess I'll call a deep well of evidence that cybersecurity is hard. We have a pretty good understanding of how important targets have a hard time defending themselves, particularly against attackers who are nation states or one notch off of being nation states. At the risk of seeming oddly self-congratulatory, I've long thought that cybersecurity is the most difficult intellectual occupation on the planet, as we have two challenges: rapid change and sentient opponents. Yet at the same time, the cybersecurity occupation, we certainly seem to be getting better and better. We have better tools, we have better understood practices, we have more and better colleagues, and that's the plus side. But from the point of view of a risk-oriented person, from the point of view of prediction, what matters is the ratio of skill to challenge. As far as I can estimate, we are expanding the society-wide attack surface faster than we are expanding our collection of tools, practices, and colleagues. If your society is growing more food, that's terrific. If your population is expanding faster than your improvements in food production can keep up, that's not so good. So it is with cyber risk management. Whether in detection, control, prevention, or any of the other characteristics, we are absolutely notching personal bests on a regular basis. But all the while, it seems that the opposition is setting the world records. As with most decision-making under uncertainty, statistics has a role to play, particularly ratio statistics that magnify trends so that the latency of feedback from policy changes is quicker to recognize. Yet statistics, of course, require measurement, and I'll return to that in a moment. I don't actually have well-vetted figures for the total society spend on a worldwide basis on cybersecurity, but it is clearly larger than ever before, yet so are the failures that we know about. According to a power law analysis of data breaches that I'm working on with a couple of others, the failures that we do not yet know about, but in time will, are likely to be worse than the ones we know about already. A week ago today, James Traynor, who is the acting assistant director of the FBI's cyber division, said as follows, that the agency used to learn about a new large-scale data breach every 2 or 3 weeks. Now it's close to every 2 or 3 days. Traynor also said that the cybersecurity industry needs to double or triple its workforce in order to keep up with hacking threats. In short, that a storm is gathering, in some sense, understood intuitively by the general public, even though the general public has become jaded to press reports about cybercrime. As it happens, my wife and I run a small business, which is irrelevant to this workshop except for one thing. Just this past weekend, one of our high school-aged employees told me that his guidance counselor advised him that the 2 best choices for what to study in college would be game design or cybersecurity, because if you got good at either of those, you could get jobs well paid enough that the student loan burden wouldn't be impossible to manage. In other words, the idea that cybersecurity matters and that we are losing has reached the level of high school career advice. As you no doubt also know, what to do about cybersecurity has also reached the highest policy levels of government. Jockeying for position and authority aside, the question of what is to be done is on the lips of a broad spectrum of government officials. Part of this is quite naturally that here in the United States, we have the most to lose from cybersecurity failures for the simple but frequently forgotten reason that we depend on the digital realm more than any other society. You're only at risk from something that you depend on. Almost a year ago, the Pew Research Center invited 12,000 experts, I'm not sure how they define that, but nevertheless 12,000 experts, to answer a single yes/no question. It was, by 2025, will there be significant changes for the worse and hindrances to the ways in which people get and share content online compared with the way the globally networked people can operate online today? Yes or no? They invited 12,000, they got 1,400 answers. So I'm put aside whether selection bias may be reflected in who chose to answer and who did not. Nevertheless, Pew found 4 themes that dominated all respondent comments. The first was actions by nation states to maintain security and political control will lead to more blocking, filtering, segmentation, and ultimately balkanization of the internet. 2, trust will evaporate in the wake of revelations about government and corporate surveillance and the likely greater surveillance in future. 3, commercial pressures affecting everything from internet architecture to the flow of information will endanger the open structure of online life as we know it now. And efforts to fix the, quote, too much information, unquote, problem might well overcompensate and actually thwart content sharing. So those were Pew's findings. My colleague and journalist Rob Lemos mapped Pew's themes to 2 alternative futures, one where cyberspace is made to look more and more like meat space, and the other where meat space is made to look more and more like cyberspace. Lemos wrote this: if cyberspace converges to our physical reality, then we will have balkanization and commercial efforts to artificially create information monopolies. While if the physical world goes toward the digital space, then we have greater surveillance, the erosion of trust, information leakage, and the reaction to that leakage. That's the end of his quotation. But more crucially, Lemos also observed that the growth of technology has greatly increased personal power. Again, quoting, the impact that a single person can have on society has significantly increased over time to where a single individual can have a devastating effect. The natural reaction for government is to become either more invasive to better defend its monoculture, or more separate to firewall threats from one another. Because threats and kinetic impacts can increasingly travel through the digital realm, they necessitate that the policy and legal frameworks of the digital and physical world do converge. So in other words, Lemos argues that convergence is an inevitable consequence of the very power of cyberspace in and of itself. I'm not going to argue with Lemos's idea that increasingly powerful, location-independent technology in the hands of the many will tend to force changes in the distribution of power. That's true by observation. In fact, that is a central theme of this essay and others, that the power that is growing in the net, per se, will soon surpass the ability of our existing institutions to modify it in any meaningful way. So either the net must be broken up into governable chunks, or the net becomes government. It seems to me that the leverage in this circumstance favors cyberspace whenever and wherever we give cyberspace a monopoly position, which we seem to be doing both blindly and often. In the last couple of years, I've found that institutions that I more or less must use, my 401k custodian, the government accounting office's accounts payable department, the payroll service that my employer outsources to, and so forth, no longer accept paper letter instructions, that the canonical wet ink signature on bond paper is not something that they will take. They each only accept digital delivery of such instructions. This means that each of them has created a critical dependence on an internet swarming with men in the middle, and which is more, they have doubtlessly given up their own ability to fall back to what worked for a century before. It is that giving up of alternative means that really defines what convergence is and does. It is said that all civil wars are about on whose terms reunification will occur. I would argue that we are in, to coin a phrase, a cold civil war to determine on whose terms convergence occurs. Everything in meat space we give over to cyberspace replaces dependencies that are local and manageable with dependencies that are certainly not local, and I would argue much less manageable because they are much less secure. I say that exactly because the root cause of risk is dependence, and most especially dependence on expectations of system state. I say much less secure because one is secure, that is to say, one is in a state of security, if and only if there can be no unmitigatable surprises. The more we put on the internet, the broader and unmitigatable surprises will become. This line of thought is actually beginning to sink in. Let me quote from a Bloomberg article a few months back. Quote, Wall Street's biggest trade group has proposed a government industry cyber war council to stave off terrorist attacks that could trigger financial panic by temporarily wiping out account balances, according to internal documents. The proposal by the Securities Industry and Financial Markets Association, which by the way is a big deal, calls for a committee of executives and deputy level representatives from at least 8 U.S. agencies, including Treasury, the National Security Agency, and the Department of Homeland Security, led by a senior White House official. The document sketches an unusually frank and pessimistic view by the industry of its readiness for attacks wielded by nation states or terrorist groups whose aim is to destroy data and machines. It says that the concerns are compounded by the dependence of financial institutions on the electric grid, which is also vulnerable to physical and cyber attack. That's the end of the quotation from Bloomberg. So here you have the biggest financial firms saying that their dependencies are no longer manageable and that the state's monopoly on the use of force must be brought to bear. What they are talking about is that we have no way to mitigate the risk of common mode failure. To repeat, risk is a consequence of dependence. Because of shared dependence, aggregate societal dependence on the internet is not estimable. If dependencies are not estimable, they will be underestimated. If they are underestimated, not be made secure over the long run, only over the short. As the risks become increasingly unlikely to appear, the interval between events does grow longer. As the latency between events grows, the assumption that safety has been achieved will also grow, thus fueling increased dependence in what is now a positive feedback loop. Accommodating old methods and internet rejectionists preserves alternate, less complex, more durable means, and therefore bounds dependence. Bounding dependence is the core of rational risk management. However, we show no signs of being willing to bound dependence. Yet if we don't bound dependence, then we invite common mode failure. In common mode failure comes exactly from underappreciated mutual dependence. Let me quote NIST on this. Redundancy is the provision of functional capabilities that would be unnecessary in a fault-free environment. Redundancy is necessary, but not sufficient for fault tolerance. System failures occur when faults propagate to the outer boundary of the system. The goal of fault tolerance is to intercept the propagation of faults so that failure does not occur, usually by substituting redundant functions for functions affected by a particular fault. Occasionally, a fault may affect enough redundant functions that it is not possible to reliably select a non-faulty result, and the system will sustain a common mode failure. A common mode failure results from a single fault or fault set. Computer systems are vulnerable to common mode resource failures if they rely on a single source of power, cooling, or I/O. A more insidious source of common mode failures is a design fault that causes redundant copies of the same software process to fail under identical conditions. End of quotation. That last part, that a more insidious source of common mode failure is a design fault that causes redundant copies of the same software process to fail under identical conditions, is exactly that which can be masked by complexity, precisely because complexity ensures underappreciated mutual dependence. And that's where LangSec comes in. LangSec is one of, if not the, answer to the question of common mode software failure, at least in circumstances where we have some idea of what we are depending upon, and thus under a common threat from its disappearance or perversion. I imagine that even in the lay world, it is understood that the more we depend on something, the more effort should have been put into making it bulletproof and or fail-safe at the outset. Take plane crashes. Plane crashes cannot be hidden, so we learn something from each one. A few months after the November 2011 crash of an airliner in Queens, New York, I had occasion to ask an FAA analyst about the National Transportation Safety Board's finding that the pilot had broken the tail off the plane. I said that I had never heard of that before. He said, "And you won't. We learn from mistakes." That's well said. On the other hand, near misses are far more frequent and generally they are not reported. That suggests that we don't learn from them. Just as the NTSB takes mandatory reports of airliner crashes, the Centers for Disease Control take mandatory reports of public health events, meaning immediate disclosure of patients who have smallpox or anthrax or the plague, but not patients who have cancer or third-degree burns. I proposed elsewhere that the force of law require reporting of cybersecurity failures which are above some severity threshold that we have yet to negotiate. While below that threshold, we follow the advice of Richard Danzig in his piece, Surviving on a Diet of Poisoned Fruit, where he made the following policy proposal. Fund a data collection consortium that will illuminate the character and magnitude of cyber attacks against the private sector, using the model of voluntary reporting of near-miss incidents in aviation. Use this enterprise as well to help develop common terminology and metrics about cybersecurity. While regulatory requirements for aviation accident reporting are firmly established through the NTSB, there are no requirements for reporting the vastly more numerous and often no less informative near misses. Efforts to establish such requirements inevitably generate resistance. Airlines do not welcome more regulation and fear the reputational and perhaps legal consequences of data visibility. Moreover, and perhaps near accidents are intrinsically more ambiguous than accidents. An alternative path was forged in 2007 when MITRE, a government contractor, established the Aviation Safety Information Analysis and Sharing System, or ASIAS, receiving near-miss data and providing anonymized safety, benchmarking, and proposed improvement reports to a small number of initially participating airlines and the FAA. That's the end of the quotation from Danzig's piece. But I will tell you that today 44 airlines participate in that program voluntarily. The combination of a mandatory CDC-like model for above-threshold cyber events and a voluntary ASIAS model for below-threshold events is what I recommend. This does leave a great deal of thinking still to be done. Diseases are treated by professionals, but malware infections are treated by amateurs. Diseases spread within jurisdictions before they become global. Malware is global from the get-go. Diseases have predictable behaviors, but malware comes from sentient opponents. So don't think this or any other proposal to ensure that we get a chance to learn from failure is an easy one or that it is devoid of side effects. Let me quote Francis Bacon. Truth emerges more readily from error than from confusion. What I am arguing is that is that we not keep ourselves in a state of confusion, but that we graduate to a state of acknowledged error. Were we to do so, LangSec would clearly be part of the solution to the puzzle of cybersecurity, as not only is LangSec a path to rigor, but also a path away from confusion. And confusion we got on several fronts. I'm working on an article about the rising undiscoverability of what is on the internet at large. There are lots of examples, like how the fraction of all reachable hosts that have a DNS entry of any kind is falling, that carrier network address translation conceals a great deal of everything, that IPv6 trees are too big to walk, and or what is an end in the end-to-end conceptualization is itself falling to the reality of virtual machines and, more importantly, containers. Put differently, we can no longer bound the attack surface in the network sense, nor can we bound it in the software sense. It is fairly clear that as applications, especially web applications, as they grow, the complexity of interactions among their moving parts increases. The HTTP archive says that the average web page today, makes out references to 16 different domains, as well as making 17 JavaScript requests per page. And the JavaScript byte count is 5 times the HTML byte count. A lot of that JavaScript is about analytics, which is to say surveillance of the user experience. And we're not even talking about getting your visitors to unknowingly mine Bitcoin for you by adding a little JavaScript library to your website that does exactly that. My colleagues over at Veracode are seeing machine-written code of vast sizes, 20 gigabytes, that contain apparent vulnerabilities, meaning even machines and machine-written code contain vulnerabilities. In a relatively recent Atlantic Monthly article, Bruce Schneier asked a very cogent first principles question. Are vulnerabilities in software sparse or dense? If they are sparse, then every one you find and fix meaningfully lowers the number of avenues of attack that are extant in the world at large. If they are dense, then finding and fixing one more is essentially irrelevant to security and a waste of the resources spent finding it. 6 take away 1 is a 15% improvement. 6,000 take away 1 has no detectable value. Which is it? In one of my recent security metrics columns, I took a stab at applying the techniques of field biology to the question of whether vulnerabilities are sparse or dense. That is one path to an answer of whether finding and fixing bugs is worth the effort. Sandy Clark, amongst others, takes a different tack, arguing that exploitable flaws still take our opponents a while to find and to weaponize, but if rollover of the code base can be accelerated, then you may be able to get the rollover time to be shorter than the opponent's reverse engineering time, in which case you win. Auto-update with the barest regression testing for operability might then supplant taking care for security, except that that would mean that the more important the code, the more important you should have it roll over. Try selling that idea to your compliance officer or the upstream bureaucrats. One might argue that LangSec is specific to errors that are sparse but unobvious. That is really a big deal in the context where every day that goes by without some colossal upheaval causes amateur Bayesians to say, see, the risk is small, and we had another day today when nothing bad happened, and that means that the probability of something really bad is monotonically decreasing. That is not true for Poisson processes, and that is not true for cyber warfare operatives doing the equivalent of mining the harbor. Let me put it differently. Our collective attack surface is increasing quickly in volume, in complexity, and in interlocking dependencies. To maintain constant risk in the context of an expanding attack surface requires commensurate decreases in points of exploit within that nominal attack surface. If we're going to double the number of applications or hosts, endpoints, then we must have the attackability of those applications, hosts, or endpoints. That is not happening. Workshop organizer Meredith Patterson gave me a quotation from Taylor Hornby that I hadn't seen. In it, Hornby succinctly states the kind of confusion we are in and which LangSec is all about. The illusion that your program is manipulating its data is powerful, but it is an illusion. The data is controlling your program. I think that's fantastic. As it happens, Hornby was one of this year's judges for the Underhanded Crypto Contest. The winner, John Meacham, writes a short enough description of the hidden exploit in his code for me to quote it almost entirely in full. This library has the very specific target of undermining the security of the Internet of Things. It was designed to be attractive to being integrated into IoT hardware platforms where it will be difficult to patch once discovered. The backdoor also has a fairly strong degree of deniability. It arises from a rare yet plausible bug. It would be very hard to establish malice as opposed to oversight on the programmer's part once the exploit is publicly discovered. The library implements the AES block cipher in counter mode, and for the most part behaves as it is described in almost all circumstances it would normally be used in. Notably, it passes all the FIPS and RFC test vectors for AES encoding and can interoperate with OpenSSL. The library can be used in most any application where AES is needed and will behave exactly appropriately. The library becomes exploitable specifically when it gets used as part of an implementation of IPsec over IPv6 in a constrained IP stack, in a resource-constrained IP stack. In such a case, under normal operation, the library will perform properly. And here's your part. Interoperating with other IPsec AES counter mode hosts. But when it is triggered by a forged ICMP v6 packet, it will lead to full plaintext reveal. Another forged ICMP packet will restore the conforming behavior so that normal packet retries will mask the improper behavior. The bug, or I would say weird machine, is triggered when an encoded stream is split on a boundary that is not divisible by 16 and then subsequently restarted. When this is done, this key schedule will be reseeded by the current IV. In practice, this will not come up due to buffers almost always being a power of 2 greater than 16 when data is split up or when an odd size is needed. It is due to the end of an encryption stream and not one that will be restarted. The compromised packets will be dropped by the receiving host as corrupted in flight due to the MAC not agreeing, and the packets will be resent with the new 16-byte aligned fragments properly encoded. By flitting back and forth between MTUs, an eavesdropper can obtain the entire plaintext of an encrypted transaction. That is precisely the thing that LangSec is all about. A weird machine triggered by a specific input in a specific set with the extra feature that a different specific input can put the system back in normal operation, attractive for integration into devices too small or distant to be patchable after discovery, and plausibly deniable. Is that prizeworthy or what? Workshop organizer Sergey Bradis wrote me saying almost the same thing. This is his quote: "Even systems for which we have constructed correctness proofs in the CAR-HOR sense, those proofs are for specific preconditions. And the proofs tend to say nothing of what and how much unwanted computation these proven pieces of code would be capable of when the preconditions do not fully hold. For reason of programmer error or some other reason, there appears to be a whole universe of unwanted computation, dual and larger than that of the intended computation, and this dark computation universe is expanding." Along with my still somewhat back of the envelope calculation of the scale of dark reachability in networks, the dark reachability in code space might be growing faster still. It would surprise me if the huge investment in offensive cyber technology were not a proxy measure of the growth in some combination of darkly reachable networks and darkly reachable code space. That offense budgets for this are growing as fast as they appear to be has to signal some degree of outcomes favorable to those who stockpile cyber weapons. As many of you know, research programs do not grow when they are not getting results. Just to pound that home, Chris Inglis, retired NSA Deputy Director, said to me that if we were to score cyber the way we score soccer, the tally would be 462 to 456, 20 minutes into the game, i.e. all offense. I will take his comment as confirming at the highest level that offense is where the innovations that only states can afford is going on, and that they have results which I'd wager are all but entirely weird machines. It almost appears that we are building weird machines on purpose. Almost the weirder the better. Take big data and deep learning. Where data science spreads, a massive increase in tailorability to conditions follows, which is a wonderful thing. But even if Moore's law remains forever valid, there will never be enough computing. Hence, data-driven algorithms must favor efficiency above all else. Yet the more efficient the algorithm, the less interrogatable it is. That is to say, the more optimized the algorithm is, the harder it is to know what the algorithm is really doing. And there is a feedback loop here as well. The more desirable some particular automation is judged to be, the more data it is given. The more data it is given, the more its data utilization efficiency matters. The more its data utilization efficiency matters, the more its algorithms will evolve to opaque operation. Above some threshold of dependence on such an algorithm in practice, there is no going back. As such, if science wishes to be useful, preserving algorithm interrogatability, despite efficiency-seeking, self-driven evolution, is the research-grade problem that is now on the table. If science does not pick this up, then Larry Lessig's characterization of code as law is fulfilled. But if code is law, what is a weird machine? Note that these algorithms do still specify a language of good and valid inputs. But as this specification is implicit and non-interrogatable, there is no way to actually verify the specification either for required properties or for correctness of implementation. This underscores what I understand to be a couple of LangSec slogans. Ambiguity is insecurity, and explicit is better than implicit. Suppose for a moment, though, that we knew how to do compliance testing for some set of LangSec principles. Would we find parser and parser differential bugs sparse or dense? What would be true in web applications? And would that be more true than in firewall code? What would we discover? Do we even know whether fuzzing is effective or how effective it is? If I fuzz the daylights out of some input accepting code and simply nothing happens, can I make the claim that the absence of evidence is the evidence of absence? Almost surely not, which is to say that execution models, including execution models for exploits, do not fall out of fuzzing. For our purposes, does fuzzing even matter? I would not count on it to estimate the sparseness or density of exploitable flaws. So does a complexity measure like maybe McCabe's cyclometric complexity tell us anything predictive about the weird machines a given code body might harbor, an upper or a lower bound on their density, say? Or is it not code complexity that matters, that we should instead perhaps look at protocol complexity? Does any protocol that has complex enough data, as Sergey said in the introduction, such as ASN1 and perhaps especially BER, does that necessarily become a fount of bugs once approached deeply enough? What did we learn from OpenSSL, from Heartbleed? John Quarterman estimates that as much as 10% of internet backbone traffic is unidentifiable as to protocol. Even if he's wrong about that measure, it is still real and a measurable percentage. What share of that traffic is peer-to-peer? What share of that traffic is coming from a test harness for finding weird machines? Is its very unidentifiability a signature for parser targeting? Some of you may know that one of the core ideas of the early internet, something known as the robustness principle, or more often as Pastel's law, read as follows: be conservative in what you send, but be liberal in what you accept. That is not exactly an engraved invitation to weird machine deployment, but you can read it that way. In 2011, Eric Allman wrote a reconsideration of the robustness principle, in which he argued that because interoperability and security are in natural tension, quote, be conservative in what you accept, end quote, likely has become the necessary rule, as the spread of the internet has, in so many words, made every sociopath your next door neighbor. Coming from the original author of SendMail, Allman's conclusion has the weight of some considerable experience. But as the cliche goes, you ain't seen nothing yet. New protocols and new stacks appear every day, or so it seems. One of the venture firms I deal with says that they are tracking something over 1,000 security startups. I've not read 1,000 business plans, but I've read a lot. There is no surer sign that we are in need of new disciplines than the body of those business plans. A great number of them are tightly bound to some very specific problem. A great number of them are, as I said earlier, part and parcel of the deep learning sort, where in the end, your choice is either to trust the algorithms or not. There is no interrogating them. Many of the business plans start from the hopeful position that anomaly detection in some sense, one sort or another, is the essential key to cybersecurity. But each of those anomaly detectors has a training problem in the form of, if we pick the wrong week to call normal, then the attacker who is already inside is now in our scope of normal as defined by our measurements. Would you go so far as to say that deriving security algorithms from data optimistically called normal operation results in a weird machine if there's an attacker already present when you take your snapshot of normality? Perhaps, perhaps not, but Trojan hardware might be easier to describe this way and with less argument. A correspondent recently laid down a crisp point of view on the economics that goes with this. Let me just quote it. Shrink wrap and enterprise license sales are slowly going away. Everything is moving to the cloud. All the major cloud providers package open source technologies in such a way that they can re-implement large chunks of it in closed source versions. The Hadoop you get in the cloud is not the Hadoop you download from Apache, even though it may start that way. The cloud makes it easy to look like open source without actually being open source. I've mentioned it before, but a lot of open source software is slowly being killed by the cloud because cloud providers generate a lot of margin on total cost of ownership, TCO, arbitrage. Most open source infrastructure software is badly architected and poorly implemented because so much of it started with the design of one person trying to solve a problem they were not experts at solving, which has punishing TCO implications at scale. So companies re-implement their own vastly more efficient versions of open source with a large disincentive toward open sourcing the re-implementations. If open source wants to remain relevant in the cloud, large swaths of it need to seriously level up their engineering game. The open source ecosystems that are being liberally adopted as is in major cloud infrastructures are the handful where the quality is high enough that improvements from re-implementation would be marginal. Postgres, SQL, or LLVM, for example. Now, you may or may not agree with that commenter's position, but he is right that what you think you're running on your hardware and what is running under the same name on someone else's hardware need only be compatible at the protocol level. The rest is opaque. I'm not here to kick open source in the behind, far from it, but the critique is real and relevant. This means, or so I think, that the central question for LangSec is not one question, but as I count it, three. What to teach, how to teach, and how to test if the teaching took hold. The what to teach part demands that you, for some value of you, come to some conclusions on what does a LangSec process or mindset or paradigm look like. As far as I know, you're reasonably close to an answer here, but you do have the difficulty that since LangSec is about a level of perfection not previously obtainable, it is a bit hard to forthrightly agree on the point where good enough is good enough. You need to teach developers how they can themselves know that they are or are not contributing to the world's inventory of weird machines. How do they know that they are doing it right? How do they know that they're doing the best they can? Do we need to approach LangSec in a red team, black team sort of way? For how to teach, the question has to do with the student body, so to speak. How do you reach the architects and the programmers of new protocols and the respective stacks that they're creating? The need to get the class into the classroom is overwhelmingly urgent. Just consider, as Sergey mentioned, vehicle-to-vehicle communications on the roadways, where soon enough, in addition to everything else, protocol negotiation will have to be present, the way it has to be present in, say, transport layer security renegotiation. You'll remember that flaw, the one that Marsh Ray found. That flaw was in a security protocol. Tightly coupling the digital world with the physical world is no joke. If self-driving cars talking to each other to make joint decisions is not pressing enough for you, then the North American power grid, generally known as the biggest and most complex machine in the world, will soon have similar issues. Five years ago, Kelly Ziegler at NERC calculated that patching a fully deployed smart grid would take an entire year to complete, largely because the size of per node firmware relative to the available power line bandwidth. That means that an ounce of prevention is worth rather more than a pound of cure. As to how to test if the teaching took hold, the LangSec community needs to attend to that and to attend to it soon. Like it or not, compliance, with a capital C, controls most security spend these days, and compliance regimes change but slowly. Something that can be operationalized by lesser lights than those in the room today has to appear if LangSec ideas are to usefully spread. You need to articulate some formalized set of development practices around LangSec compliance. While all this is going on, I have a question to ask. Is cybersecurity permanently offense dominant? DARPA's Cyber Grand Challenge may answer that question in part at this summer's DEF CON, where a completely robotic capture the flag contest will be held. My money is on the offense, and offense dominance as a fact of nature. If I am right, then the selling point for LangSec becomes a relative one. Those who adopt what you teach make someone else's code the code that is more attractive to attack. That is probably the best you can do in the medium term, but it is not nothing. It is said that there are 5 phases of technical maturity for any new line of thought. They are as follows. 1, you have an idea. 2, you can actually make it work. 3, you can convince someone else to try it. 4, people stop asking you why you are working on what you are working on. 5, other people start getting asked why they aren't. In my estimation, LangSec is roughly at step 4. You're not getting much in the way of why on earth are you working on that? You have a way to go before you get to step 5 and other people get pestered about why they're not and why they can't be bothered to try. For that, you need some successes. particularly if anyone reading about them says to themselves, hey, I could do that. I think that's where you are. As I said at the outset, this is hard and important, and they probably go together. There's never enough time. Thank you for yours.
Thank you, Dan. That was a very rousing keynote. We have the opportunity to ask questions. We have a roaming microphone in the back. Let's have questions from the audience.
Darren Highfield, thank you very much. Very inspirational, thought-provoking ideas here. One of the ideas that you presented that resonated was the idea of code as law, and that I think there's an important difference between human and machine interpretation that maybe we have not quite focused on enough. In other words, we've always had law, and we've always had people that have figured out weird machines in law and use them to subvert societal expectations. The way that we have combated that is actually orthogonal. It's not through analyzing the law. We may fix it ultimately through analyzing the law and producing another law or modifying it. But the way that we catch the error is by human reasoning and by using our capacity to, on the fly, adapt our interpretation of context. Our ability to say, hey, we hadn't thought about this surrounding or that surrounding. So we use a nonlinear, distinctly human response to catch the error. Whereas in LangSec, I believe we're going further down the path of rigor and precision rather than going nonlinear. So does that present us some inherent challenges in that we're playing the game of the attack and playing by the attack's rules rather than changing up the rules and detecting the attack orthogonally?
Okay, let me. Are you done? I'm sorry, I don't mean to cut you off.
Yes, no, thank you.
Yes.
Two things I would say about that. One, in the process of discovering flaws, I think the best statistic is the Verizon Data Breach Investigations Report, where they say consistently now over, how long have they been doing that? 6 years? Consistently that 80% of data breaches are discovered not by the victim. They're discovered by somebody else. And that's worth noting in that it isn't that the person who has experienced the loss is the one who finds it. Part of that, of course, is the unusual physics, if you want to call it that, of data, which is if I steal your data, you still have it. Whereas if I steal your car, it's a different matter. The other is we are not just in cyber, but in other areas as well, beginning to have, I think what you're getting at. A year and a half ago, I had the opportunity to ask Larry Castro, who is retired deputy director of the NSA, what he would be worrying about if he was still in his old job. He said, well, today I'd be worrying about the maker crowd, especially the drone guys. And tomorrow I would worry about do-it-yourself bio. Now that's not us, but I think they are parallel in the sense that the drone crowd is producing a set of use cases for which we don't have any rules. The do-it-yourself bio folks could produce a use case for which a rule might be a little late by the time you discovered that something had escaped from the lab. Cyber just happens to be of the same sort, I think. By the way, I use the word cyber, not because I particularly love it, but because I work in Washington and you have to use the language that you work with. That's just how it goes. You're right that expecting us to have one mechanism that both prevents and discovers, if I'm getting your point correct, that having one mechanism that both presents and discovers is asking rather a lot, that you need something orthogonal, or if you will, that doesn't have a common mode failure with the very problem that you're looking for. With data breaches, the fact that someone else finds your data in the wild is indeed, I guess in this sense of the word, orthogonal to whether you notice that you lost it. I worked at a hospital once upon a time. I worked at a lot of hospitals, but, and this is a 10-year-old story that's very short. This particular hospital went to update its mainframe. Something went wrong and they had to back off. And it turned out they didn't have a good back off procedure. So they were down for 4 days. This is a hospital, Mike. And so what they did was they reverted to paper for example, ordering lab tests. The old doctors thought, oh, well, sure, no problem. I'll just use paper. I'm used to that. The young doctors couldn't figure out how to do it. And that is an example of one set of users, in this case, old doctors, had an orthogonal, if you will, a non-common mode failure mechanism for, oh, I know how to order lab tests this way. You check the boxes, you write this number here, and it works. Whereas the young ones had never done that before. They were used to doing it on touchscreen, and it took them a while to cope. Now you might say, well, that's a trivial example, but it's a real one. So it's been written up and all of that. I think you're onto something, and I don't know quite what the answer is, but you are correct to guess that, or we are both in the same corner guessing that a mechanism for prevention and a mechanism for detection probably ought to have very few similarities and not be connected such that the failure of one is the failure of the other. I guess maybe firewalls are a counterexample or something.
I might try to add to that. Interestingly, what we see with protocol design is that the more you front load the understanding of what you're going to exchange, the simpler you make it, the less of a problem you have later. So the protocols that basically were supposed to be everything for everyone down the line and expanding and filling all kinds of niches did not do so well. Building on them ended up like building not just on sand, but on quicksand, right? So
I forget who said it, but somebody described the standards process as having a threshold above which it doesn't matter if you add more features, because what's one more feature? And the object was to keep it below the threshold where the urge to add more features was irresistible.
well, yes. But you see, in order to lay a proper foundation, in order to not lose the security game, the moment you chose an overly complex protocol, forget about the implementation. The implementation is doomed, right?
Yeah.
It's the implementations have been doomed by syntax. With SSL, we're seeing that. With ASN1, we're seeing that. And who knows with what other protocols we will see that. But this sort of a situation where you have to front load all of this design and all of this simplicity and not rely on subsequent interpretation that has been a feature of law, that is a feature of the precedent system, right? In a sense, you are subsetting law by precedent, the same way you're subsetting your firewalls, your traffic by your firewalls, and you're subsetting your application protocols by application proxies, right? You go to a smaller language. Well, you should probably start with a smaller language. to begin with.
Don Davis, who's a friend of mine, was a compiler guy. And I can't quote his thing exactly, which is unfortunate because he said it better than I did. But he said when you're designing a language, two things you should avoid are order-dependent syntax and recursion. He said both of those are attractive to experts, but when you use them, you inevitably come to a point where non-experts find that the easiest way to get their job done is to special case the circumstance where they are today. And after that, no one can ever understand the entire system again because of the special casing. So it's a compiler person, but he was arguing to avoid two things: order-dependent syntax and recursion.
And interestingly enough, this chimes with our rants against context-dependent, arbitrarily nesting languages. So both of those recommendations have a very specific place on the Chomsky hierarchy scale, and have been are probably deserve their own common weakness enumeration spot. Mm-hmm. Yeah, more questions.
Michael McCarron from the Naval Postgraduate School. You touched on a concern related to big data and increasing need for scaling up computation. So this may be a naive question, but MapReduce seems to give an example where a goal to achieve greater efficiency through parallelization has provided some incentive for design simplification, at least the interface as presented to the developer. So is there some hope that a need for greater efficiency would not always be in conflict with the design, or with the desire to sort of simplify your design, at least in some cases?
Well, there's always hope. I don't know the answer to your question. I'm sorry, I don't know the answer to that. I will say, everybody my age came to cybersecurity from somewhere else. I happen to have been trained as a statistician, but that's irrelevant most days. It just happens to be how I got here. I will say, if you're building large models, one generally early on has to decide, am I building a model whose purpose is to explore causality? Or am I building a model whose purpose is to achieve control? If it's achieve control, it doesn't matter in some sense how many variables you throw into the mix, because the coefficients in the equation don't matter. What matters is the precision of output compared to reality. If you're going for causality and you have 3 or 4 variables which are actually measuring the same thing and you don't know it, you'll be led way astray by the coefficients that fall out of the curve fitting or whatever process. So my guess is an awful lot of the big data deep learning regime is measured by its capacity to do whatever work product you thought it was going to do. You know, Watson playing chess, for example, or I didn't know until just recently, Watson writing a cookbook, for heaven's sakes. If that's what you want, don't pay attention to the coefficients. You can't pay attention to them because they're meaningless. But on the other hand, that is the very thing that I was getting at in a different word, interrogatable. Michael Osborne at Cambridge University, that's his word. I stole the word from him. When you get the paper, you'll see I actually give a reference to that. If you want an algorithm to be interrogatable, that is to say, you want the parts of it that make decisions to be ones where you can look at it and say, I know what it's doing here, then you do have to be careful about the data that you're putting in, because the data is, just like the Hornby quote, controlling your program. I guess my answer then is a waffle. I'm waffling about what problem do you think you're trying to solve? And again, if you're a statistician would say, are you going after causality or control? You can't do both.
Jacob Torrey, AIS. Great talk. There was recently a keynote by Alex Stamos from Yahoo, a CISO of Yahoo, where he makes the claim that AppSec is eating security, in the sense that at scale, especially at the 10 gigabit per second network, a NIDS or a firewall has about the same amount of times it takes a photon to travel from a 6 foot tall man's foot to his eye to make a decision about whether or not to accept or reject a packet, and so we need to move closer to the application. Would you say that LangSec is eating AppSec, or are there other parts that are missing?
I'm sorry, there's an echo in what you were saying. Sergey, I hear you well at the front. Could you repeat that enough for me to, sorry.
So the Alex Stamos in Alex Stamos keynote about AppSec eating security. The idea was that the firewall has a tiny amount of time to determine whether to accept a packet or reject it. Again, I would say that this plays perfectly into our view of things, that rejecting or accepting a packet should be done with least context and with least amount of computational complexity, which of course is a matter of syntax. But the question was that, well, will LangSec eat AppSec? Or the other way around?
Well, I think we need to put some money on the table here and start making bets on that. Well, let me draw a small analogy. If you're trying to test for a rare but terrible disease, and you have a limited budget, which I guess you could think of as dollars or time, two-stage testing is frequently what you would turn to, where the first stage says, I want to rule out as many individuals as possible. In other words, I want to say this packet is not harmful. And what you want is something that has no false negatives, and you want it to be cheap. If it has no false negatives and you got a negative and it's cheap, pass it along. You then have a second stage, which has no false positives, but can afford to be more expensive because it's seeing less. It has less work to do. That's how, for example, AIDS testing in the blood supply is done. You know, when people give blood, that's how it's done. You're looking for a first stage, which is cheap, with very low or no false negatives. You're looking for a second stage, which can afford to be more expensive so as to get low or no false positives. And maybe that's the answer. Maybe I'm thinking out loud here, but maybe something two-stage is what you might want to consider. Is there a LangSec version, just to pick on the fact where we are at the moment, is there a LangSec version of a two-stage process?
Well, so I might respond to that. We have exploits we have weaknesses vulns that are driven by syntax, and we have vulns that are driven by semantics. The ones that are driven by syntax recognition have no business existing, right? Separating semantics.
So if I may say so, in what I was just saying, if you say this has a syntax error, throw it away because there's no false negatives, so to speak.
Yes. So syntax should be unambiguous. Syntax should be a parser that checks correctness of syntax should be validated and verified. It should not have any ambiguity as to what is correct syntax. It should use the least amount of state to determine what is correct syntax. Now, semantics is a different matter. Semantics, if we can't try to eliminate all of the errors of validating syntax. In order to deal with semantics, well, you have to solve the halting problem. And we're not in that business, unlike, some security companies that judge all kinds of inputs. And
Well, I've certainly seen company business plans that involve, for example, in a way, the same spirit as nonstop computing. They involve running a bit of code that you got JavaScript or what, I'm just picking on JavaScript because it's convenient. Running a little bit of code or analyzing some packets in more than one machine at the same time with different preconditions. And if you get the same result from all three, say, that's a different conclusion than if a different set of preconditions in 3 different machines running the same code at the same time produce different results. Now you realize that it is dependent on the preconditions. What do you want to do with that? And I don't remember either the names of the companies involved, but I've seen that of recent time.
Well, so you basically, that is the model of computation we might call the sacrificable twin.
Sure, sure.
Separating syntax and semantics is hard, right? For example, nested links, whenever they are treated as semantics of payloads, we have a disaster. So everything that has to do with how the data objects nest in each other has to be where the boundaries are, has to be syntax. True semantics waits until the syntax recognition is done. So I think that the way of separating the low cost and no false positive checks and the further checks would be exactly on this border. And LangSec would belong exactly in the syntactic part of it. Syntactic recognition. That would be my take on this.
Mm-hmm.
How are we doing on time? Yeah. More questions? Yes.
Hello. This is Kevin Fall. Hi, Dan. I haven't seen you in a few years. Question, so this partitioning of processing, right, the history of firewalls came because there was heterogeneous capabilities at the end stations. And so you needed to put something in front because you couldn't equally protect all the stuff behind it. So if you're going to talk about partitioning the overall processing required, how do you know with a heterogeneous set of end systems what the total aggregate amount of processing is required to feel safe? Further, given that we don't actually have communication in general between the firewall and end station to know what the sum of processing across the two have been.
I don't have a good answer to that. The how do you know question comes up in a lot of this. I'm going to punt on that and think about it. That's a good question.
So your example of, I guess, AIDS blood. So imagine you had a world in which your firewall processing annotated the results so that your end system noticed, like, some measure of what's been achieved so far so that it could know, or you could, from another vantage point, make that assessment. But right now we have no connection at all. No processing really do we get in the application. Have we been told to what incremental point we've achieved analysis up to there?
So you would, for example, have the firewall pass on, I'm sending you this message, I'm not sure about it, I've had to discard a bunch others from this direction.
Something like that, yeah.
And do be careful.
Or you need to be this careful because I was only able to look at it. I was only in your how much resources you've expended. I've only been able to expend this much time. And we know from results that there's only this much type of analysis that can be done under that condition.
In rough analogy, like a spam header on an email.
Yeah, kind of, right.
Well, I pay attention to those, but then again, I write my own filters. You probably do too. That's an interesting idea. Whether you can do it at scale and speed. If there's anybody in the room from one of the obvious places, Amazon, Google, Facebook, or whatever, perhaps they could answer.
There's an analogy for code. So the code has been through this much formal analysis and this much testing and this much model checking. And so I have a write-up of some sort of how much vetting has been done up to this point. And now you can make a risk-advised decision for deployment under what conditions.
Well, a counterexample might well be, what do the high-frequency trading people do when they have no time to do anything, and a nanosecond or 3 or 4 makes the difference? That stuff is running completely naked at all times. I don't know that anybody has actually tried to do something destructive there. I mean, most attacks in that circumstance are, can I take the money? Even if the money comes in mighty thin slivers. Nevertheless, they're running in a completely naked environment. I guess probably with a certain amount of attribution, but that doesn't help if you're in the middle of a flash crash, which of course is a weird machine at scale.
We,
Um,
yeah. So that,
rereading the analyses of the flash crash, or I guess what, we've had 3 now?
we're about to
Rereading
find
the
out because they're
analysis of
gonna.
that might well suggest a parallel answer to your question.
I guess incremental evidence is the thing I've been thinking about a lot.
Yeah, incremental. Again, I don't have a solution. I'd like to have one, but I don't. You gave me something to think about.
Another question. Hang on. Hi there, this is James Sullivan from University of Calgary. So I just wanted to add on to the previous question. So the fact that in the firewall example, the firewall doesn't really have implicit communication with the inner hosts about what it has already done to the inputs. Do you think that that's sort of an interface that is really undefined between the two and it's causing issues in and of itself? The fact that there's no implicit communication as to what processing has been done on the input?
Do I think that it's an unsolved problem? Is that what, I'm sorry, the
Well,
echo
what
is
I'm saying is that do you think that that is a source of issue? Or do you think it's an interface that we haven't defined properly? And do you think that's a source of?
Well, I think if somebody is claiming to protect you, whether it's a firewall or whatever, if somebody's claiming to protect you, and they have a sense of whether they have done a perfect job or none at all, or more to the point, something in the middle, I think it would be useful to pass along how well they thought they were doing. Maybe they don't do it with every single packet. Maybe they do it in some other sense, a running meter or the like. That idea is a very interesting idea. I'm just having a hard time thinking about how to operationalize it right off the bat without breaking things. But is there a way to pass along this is like having a margin of safety. Can you pass along a statement? Can you actually calculate a statement of the sort of the margin of safety for this is something or other, or is no worse than X, or is as clean as the driven snow, or that's just a very interesting idea. I'm not trying to dodge. I'm just trying to think of the implications of that.
So this is Meredith, Dan. One thing that occurs to me is this actually kind of ties into what I was saying earlier about eliminating strings and introducing types. You could say that if you're annotating, a partially parsed packet with some information about that, you could basically just ball that up into a type that carries what information you already, because you know what you have some set of annotations that you will be placing on packets as you send them along, which is essentially an enumeration. So you can make types out of that. And this, I see some similarities as well to proof carrying code. I remember back in 2011, Len was talking about the idea of could we define grammar carrying code, input handling code that that can verify that yes, it is handling this grammar.
You just suggested something. You just made me think of something. Again, I have the tendency to get stuck on a question and chase it down. In an IPv6 world where multi-homing is inherent in every device, would it make sense to pass a clean and a unclean stream to an endpoint that you'd say, I think this is good, I'm not this is what it came from? I mean, that in a way is dodging and saying, I don't know, you make up your mind, here's what I think. Would passing both ever have value?
Here's the parsing differential. You deal with it.
Yeah, sort of. Yeah, here's a differential, you deal with it.
So Michael Lucas, let me just augment this. So I think it's an interesting
You know,
problem.
that's a dodge. Don't get me wrong. That's a dodge. I mean, it almost sounds like it's written by a lawyer, but
You're actually increasing the complexity of the problem here because you're
yes, and
telling
I'm
the end
completely-
host, hey,
exactly.
you have a
So-
new
so
parsing
the-
problem.
The
to
jury
do.
will disregard what I just said. Sorry.
So Dan, Michael Locaster here. I have a question perhaps on compliance. You spent a little bit of time talking about compliance, how to show that a code base might have some LangSec compliance, and you threw it back on us to come up with those principles. But I think there's a very practical problem involved here. So I routinely stand up in front of a class, and when I tell them about LangSec, and I say, LangSec is great, rah, 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 but they graduate and they get jobs where their job is to get a bit from point A to point B. And that's the measure of success, not let me draw a formal grammar of how I'm achieving that, right? This just simply doesn't come into consideration. So how do you change the incentives in the industry? Right.
Well, you know, we have a long history. Again, I struggle with analogies sometimes just to think, have we seen a problem like this before? We have a long history of saying you can only have so much poison in the fruit you buy. And over time, we have lowered that and lowered that and lowered that. You know, now we're talking, you know, parts per trillion of various things. I'm not eager for a regulatory approach, but I'm thinking, is successive improvement in purifying, if you want to call it that, purifying data streams, an approach that we might take? You know, we've done that with edible things. We've done that with fuels. We've done that with lots of things which are, in some sense, the water of modern life, where we say, well, at the current time we can detect, you know, this, and therefore it has to be clean to this standard. At a later time we can detect better, and therefore we decide that it has to be clean to that standard. This goes back to something I said in my talk, which is, I don't think we can make progress, we, and if you don't mind my using the word we to mean the people in that room and me at this end, I think we can make progress here, but we're going to have some way to test, if you will. And the test vectors that appear in things like FIP standards and so forth are not the answer.
Right.
As witnessed this lovely winner to the underhanded crypto contest, where it passes all the vectors. And it turns out, in that case, to even have I can open the door and I can close the door, so you won't even know that I opened the door and closed the door while I was looking. Can we make progress on saying whether something is consistent with the LangSec idea? And the minute we can do that, I think then we can start ratcheting up the question of, and what should this technique we have discovered, what should this technique be applied to, and how vigorously and with what rule of, I'll say law, but I don't mean it necessarily in the sense of the legislature. I think to make progress, we have to have that.
So I might propose what I proposed for the workshop for the building code of medical devices. You know, houses have building code. Why not other physical devices that, well, some of us get connected to every now and then? So merely asking where the recognition of inputs stops and processing of the data starts, showing where you have validated your input data, showing that on the code, that bright line. If you can't show it, if you can't show the point after which you believe specific assumptions about your data, then perhaps you have not passed the building inspection.
So that's, if you will, level one. Level two might be something else, but if you can't say where parsing occurs, or the answer is everywhere, why not? If you can't do that, you're at zero. You're at one if it's all in some place that you can point to.
Yeah.
You're at two if the thing you were saying before, Sergey, if you're at two if you know that syntax and semantics are handled separately, and one of them has no sympathy. The syntax checking has no sympathy. And maybe there's a third one. Maybe that's the way you build how to tell if you're doing the right thing.
Yeah. Well, another approach could be make it worthwhile for the programmers to actually write the parser at the same time they write the grammar and in the same lines of code. So Hammer, the parser construction kit, promotes the parser combinator style, which essentially means that your parser ends up looking like your grammar. Your parser ends up looking like a collection of those productions. And then, of course, the question that just fills your mind when you look at OpenSSL code and similar kinds of code, what on earth could this a bit of pointer arithmetic salad possibly expect as a valid input, right? Then that question goes away. When the when the kind of input, when the structure of input, valid or expected input, is obvious from the code, when the code looks like the grammar, then you're probably ahead of the game somewhat. And this code is easier to maintain. And hopefully it takes you less time to implement even, and certainly less time to debug. And it saves you the heart bleeding kind of, or GNU TLS hello kind of, or other kinds of embarrassment.
I know people in various of the static analysis companies, and I know that they had a hard time figuring out how to catch things like heartbleed.
Well, so any more questions from the audience? In that case, let's thank Dan for joining us for this keynote.